So last time we met, we were talking about probability. We looked at, we did not get a chance to look at this dice example, but we don't need to. We're going to learn that the classical method of computing probability is to compute the number of ways that a certain event can occur, then divide that by the number of possible outcomes, period. So we're going to say that's called the probability of the event E, P of E here. Probability of the event E. It's the number of ways it can happen divided by the number of possible outcomes. If you flip a coin, there's two outcomes, heads or tails. If the event you want is getting a heads, there's only one way that can happen out of two, so there's a 1/2 or 1/2 probability of getting a heads. If you look at the sample space for rolling a pair of dice, this is a very famous sample space here. You roll a pair of die, you can get 1, 1. You can get 1 on the first die, 2 on the second die, 1 on the first die, 3 on the second die. So technically the way that it's written out is that you basically pretend like you throw one die just a hair before you throw the second die. And so we call one of them the first die, we call the other one the second die. And so it turns out there's 36 possible outcomes. 6 on the first die, 6 on the second die, 6 times 6 is 36. So there's 36 possible outcomes. So if we were doing a probability calculation off this, 36 would very likely be our denominator. Now, if we do throw these fair-sided die, this pair, we need to say, what's the probability of rolling doubles? Doubles, of course, gets you out of jail in Monopoly. It also lets you go again if you get doubles and you're not in jail. Doubles just means you have the same number on both die. So the double possibilities are 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, and 6, 6. So out of 36 possible outcomes, 6 of them have us getting doubles. Thus, the probability, assuming all these outcomes are equally likely, the probability is 6/36 of getting doubles, which reduces to just 1/6. So it's pretty straightforward. How this operates. 1/6, of course, becomes 0.1666666, or 16.67% if you round it to 2 decimal places and convert it to a percent. Another interesting example is if you took a standard 52 card deck, say you were playing some poker. Poker's a lot of fun. Or maybe you like, there's all kinds of games you can play. You can play blackjack. I love playing some blackjack at a casino back when, casinos were open. And casinos are great because they are really just a ton of probability experiments all going on at the same time. Even slot machines are probability experiments. So casinos are simply excellent examples to pull statistics and probability problems from. Just are. The way a standard deck of cards work is that there's 4 different suits. There's spades, hearts, diamonds, and clubs. So you have your 4 different suits. Within each suit, you have 13 different what we call face values. You have the ace, which can be low or high depending on the game you're playing, or it could just stand for 1. And then 2, 3, 4, 5, 6, 7, 8, 9, 10, then jack, queen, and king. And all of those are in this same clubs suit. Then you have your diamonds, the red cards, hearts, the other red suit, and spades, the other black suit. So As you can imagine, I mean, if you put 52 cards all together and you shuffle them and you completely shuffle them really good, and then you draw one card off the top, we're going to assume that getting any one of these cards is equally likely. So the probability that you get the 8 of diamonds, how many 8 of diamonds are there in the deck? Just one. Yeah, just a single 8 of diamonds. So the probability that you'll get the 8 of diamonds is 1 in 52. 1 divided by 52, literally the fraction 1 over 52. The probability of getting a heart, well, you can immediately just say 1/4 because that's 1 out of the 4 suits. Or you could say out of 52 cards in the deck, you can count them up and you can see that 13 of them are hearts. So the probability of getting a heart is 13 over 52, which reduces to 1/4, aka 0.25, aka 25%. All right. Let's give myself a little more space. The probability of getting an ace, there were 13 hearts, so this one was 13 over 52, but there's only 4 aces. There's only 4 aces in the deck. So then the probability of getting an ace is 4 over 52, which reduces to 1 over 13. Now 1 over 13 is not going to be nice and clean. It's going to be about 0.0769. Yeah, the decimal is usually the preferred way to express probability. Simply because when it's in decimal form, you can do math with it. When it's in a percent, you can't do any math with it. You're going to have to convert it back to a decimal in order to do math. So, yeah, pretty much. The decimal form is usually the supreme way to express probability. Finally, the probability of getting the ace of hearts. Well, there's only one ace of hearts out of a deck of 52 cards. So that becomes about 0.019 or about 1.9%. And, you know, round to however many places your specific problem asks for. The last type of probability, we will not spend too much time on this at all, is subjective probability. We already looked at empirical probability, where if you ran an experiment, say 10,000 times, say you flipped a coin 10,000 times because you were really bored, and you got 5,300 heads, then you'd say the empirical probability of getting heads based only on that experiment is 5,300 divided by 10,000, which comes out to 53%. But it would seem that the probability you should be getting heads is actually exactly 50%. So that's the breakdown between theoretical and empirical probability. But there's one other type of probability called subjective, and it's just based on personal judgment. And frankly, it's the kind that you're most likely to deal with on a day-to-day basis because you're just kind of thinking, oh, I think it's, you know, there's a 10% chance I'm going to hit traffic if I go to when I drive to work today. But it's not based on anything. You haven't calculated anything. You haven't brought in any data, research, facts. It's just kind of your memory of things or how you view them. It could be that there's a much lower chance of that. So subjective probability. Okay, so that's it on that one. Now let's bring up our next set of slides of information. We have to deal with the big or, O-R, the word or. What does it mean in mathematics and probability? Technically, whenever you're dealing with logic, mathematics, things like that, the word or really means in plain English and slash or. So when we say this or that, we mean that one or the other could happen or they both could happen. That's what we mean with the word or in mathematics. Now there's a pretty simple formula for it. This is actually the same formula on top and bottom, but this bottom one just uses set notation. It just uses a different notation. It uses the union symbol for or, which is exactly what it is. It uses the intersection symbol for and, which is exactly what it is. So whichever one you memorize, if you are comfortable memorizing that first one, then go for it. C'est la vie. So there's this kind of formula for it. This is the probability of one event or another event occurring. So let's think about it. There's a couple possibilities. Let's see who's still alive in baseball right now. It's the Rays and the Astros. In the ALCS, hopefully the Rays win because the Astros are cheaters. They're evil, evil cheaters. And in the National League, I believe it's the Dodgers and the Braves. So let's say it ends up being the Rays playing the Braves in the World Series. You could ask all kinds of questions. Now, the basketball season just ended, but let's say before it ended, it was the Lakers and the Miami Heat playing each other. You could ask the question, what is the probability, and I'll just do a new whiteboard here. You could ask, what is the probability that the Lakers win the NBA Finals, assume they haven't finished yet, or the Rays win the World Series, which is baseball? So what you can do is you can let L be the event of the Lakers, the LA Lakers winning the NBA Finals. Now they literally just won the other day, but again, we're going to pretend like that hasn't happened yet. You can let R be the event that the Rays, the Tampa Bay Rays, go away, winning the World Series, winning the baseball championship, which that's still going on right now, not the World Series just yet. It's about to start. So then what you could do is you could frame your question here. What is the probability that the Lakers win the NBA Finals or the Rays win the World Series? The way you can rewrite that is, what is the probability of L, Lakers winning the Finals, or R, the Rays winning the World Series? And it doesn't matter what our opinions of each of those are. This is always equal to the probability that the Lakers win the Finals plus the probability that the Rays win the World Series. But then something weird happens. You got to subtract off the probability that both the Lakers win the World Series and, the Lakers win the Finals and the Rays win the World Series. And the reason you have to subtract this part off is that the probability that the Lakers win the Finals already has embedded into it the chance that the Rays also have won the World Series. But the probability that the Rays win the World Series already has embedded into it the possibility that the Lakers also happen to win the NBA Finals. So if I just add these two quantities together, I'm actually double counting this thing right here, the probability that both of them win. So I need to subtract it off once. We want a single counting of it in there, but not a double counting of it. So I subtract it off once. And this is exactly, now all they did was they used this symbol and this symbol to represent or and in that formula over there using set theory. If you've taken Math 1332, you're totally comfortable with these symbols here. Okay, back to it. So let's look at this spinner. Let's say you take this spinner, you have a little thing in the middle, you flick it, and it's going to go where, and it's going to stop randomly at one of them once friction overpowers its movement and stops it. Just by looking at the picture, we're going to assume that all 8 of the slices on the pie here, the picture here, are equal sized. Thus, we're going to assume that getting any one of these numbers is just as likely as any other. Just by looking at the picture, what is the probability of spinning an even number or a number greater than 5? So look at the word or. Well, let's just count. Let's count up all the spaces that are either an even number or a number greater than 5. 1 isn't going to do it. So let me get out my pen. I'm going to put a little check mark next to the numbers that will satisfy that. 1 doesn't do it because it needs to either be an even number, which 1 is not, or a number greater than 5, which 1 is not. But 2 will do it. 2 is at least an even number. 3 won't do it. 4 will do it. 5 won't do it because the number has to be strictly greater than 5 or even. 6 will do it. It's both even and greater than 5, so it definitely gets the check, but it doesn't get anything extra special because it's both of them. It just still gets a single check. 7 will do it because while 7 is not even, it is a number greater than 5. 8 will do it because 8 is both a number greater than 5 and an even number. And so now out of 8 possibilities, there's 1, 2, 3, 4, 5 that go our way. Thus, just looking at the picture, the probability is 5/8, which reduces to 0.625. Just gonna move this over a tad. 5 out of the 8 slots or spaces correspond to what we want. All right, now let's erase these check marks. So we've already done the probability calculation, but just out of curiosity, let's see it a different way. Since we use the word or, that means we can apply this formula. What's the probability that your number is even or the number is greater than 5? The probability of getting an even number, well, let's see, there's 1. So all we're doing when we find the probability of being even, we're just honing in on it being even. We're, for the moment, ignoring the greater than 5 thing. All we want to know is what's the probability you spin the thing and get an even number. Well, there's 1, 2, 3, 4 even numbers out of the 8. So that's 4 out of 8. Now you could have just said 1/2, but I'm going to leave it as a denominator of 8. So let's see. I'm going to go ahead and put red check marks on all the ones that were even. No, not green. I explicitly told you to do red. I'm clicking red. It doesn't even want to change the color. Hold on. You are bad. There we go. Okay, so I'm going to put a red check mark next to all the 0, huh? Okay, I'm going to put, I'll make my own check mark, a red check mark next to all the even numbers, 2, 4, 6, 8. 4 out of 8 is the probability of getting an even. Now, wipe our memories for just a moment. We've already written it down. Next, I'm going to put an orange check mark to all the numbers that are greater than 5, strictly greater. That's this one, and this one. So the probability of getting a number that's greater than 5 is 3 out of the 8 spaces. So I do plus 3/8. But if I just add these two values together raw, look, I've double counted the 6 and I've double counted the 8. That's not going to fly. So now what I'm going to do, I'm going to put a purple check mark next to all the values that are both even and greater than 5, which is 6 and 8. And actually, I'm going to put the check mark over the orange. I'm just going to put a little marking here that I'm going to make up. I need to subtract this off so I'm not double counting, and it looks like there's 2 out of 8. And now 4 plus 3 is 7, minus 2 is 5. It becomes 5/8, which is exactly what we found just by doing it kind of logically. Just by thinking about the scenario logically. The problem is that you're not always going to see problems where you can just paint the picture of what's going on very clearly and easily. Sometimes you are going to have to appeal to these formulas. And we'll ignore that. When two events can't occur simultaneously, they are called mutually exclusive. Think about what some mutually exclusive events could be. The event of getting an even number on this spinner and the event of getting an odd number on this spinner, those have things with no overlap. So you can't get both an even and an odd number on this, so those are mutually exclusive events. What we're going to find is that if two events, E and F, are mutually exclusive, they cannot both occur. It is impossible. The event of getting an even number and the event of getting an odd number are not going to overlap with each other. So what we would say then is that the probability that both E and F occurs has to be 0 if they're mutually exclusive. That's another way of saying it. It's impossible for them both to occur. This also means that if you go back up here, if it was the case that E and F were mutually exclusive events, this thing would just be 0. So when E and F are mutually exclusive, all you have to do is add their probabilities together if you want the probability of E or F occurring, because there's nothing to subtract off. In fact, we now appeal to that down here. Let's say you have many events going on. You have events E, F, G, H, I, J, K, all the way down. You have as many events as you want, but any two of them are mutually exclusive, aka disjoint. Any two of them have no overlap with each other. Then the probability of E or F or G, all the ORs combined, is to just add up each of their individual probabilities. As an example, what is the probability that a randomly selecting housing unit over here has 2 or 3 rooms? So we did a survey. We found of all, maybe the entire US population. We found certain housing units, and 0.01 or 1% of them have 1 room in them. 3.2% have 2 rooms in them. 9.3% have 3 rooms. 17.6% have 4 rooms, and so on. Then you have your really, bourgeois mansions down here. What is the probability that a randomly selected housing unit has 2 or 3 rooms? Well, in this particular case, you can get away with simply adding these two together. But that's because the event of having 2 rooms in a housing unit and the event of having 3 rooms in a housing unit are mutually exclusive. You can't have a house that both has 3 rooms and also has 2 rooms in it. That doesn't make any sense. And you can't say, well, what about if they have a study? We're just going to say that's either you're going to count it as a room or you're not. So here you would just add their 2 probabilities together. And it looks like you'd get 0.125. What is the probability that a randomly selected unit has 3 or less rooms, 1 or 2 or 3 rooms? Well, since they're all mutually exclusive again, just add now these 3 probabilities. 1 or 2 or 3 rooms, add them up. What is the probability that a randomly selected housing unit has 5 or more rooms? Add up all these together. One thing you can't do is what's the probability that a housing unit has 10 or 11 rooms? You can't do that because this is just 9 or more and you don't have data on 10 rooms, 11 rooms, 12 rooms, etc. But yeah, add up all these and you got the probability of selecting a housing unit that has 5 rooms. We can do some card examples. If one card is randomly selected from a well-shuffled standard deck, find the probability of getting a king or a queen. Well, we have the word or. So this is going to be the probability of getting a king plus the probability of getting a queen minus the probability of getting both, and I'm just going to have to write it in text, a king and a queen. I'll move it all over here. Just using the word or we see there. Well, the probability of getting a king, 4 out of 52. 4 of the cards are kings out of 52. Plus probability of getting a queen, also 4 over 52. Minus, what is the probability of getting a card that is both a king and a queen at the same time? There isn't. There's no card in the deck that is both a queen and a king. It's impossible. So these are actually mutually exclusive events. So we could have just ignored this part had we already known that, but it doesn't make this formula wrong. This formula is still perfectly correct for any or probability. It's just that sometimes this will just be 0. So we get 8 over 52, and you can compute that to whatever decimal place you like. The probability of getting a diamond or a 5, well, the word or is in there, so that's the probability of getting a diamond, plus the probability of getting a 5. This is sloppy notation, but it works. Minus the probability of getting both a diamond and a 5. So let's try each one of these individual things together. The probability of getting a diamond, well, there's 13 diamonds in the deck out of 52 possibilities. So it's 13 over 52. Plus the probability of getting a 5 in the deck, there's 4 5s. So that's a 4 over 52 probability. Minus the probability of getting both a diamond and a 5. Well, actually, there is a card in the deck that is both a diamond and a 5. The 5 of diamonds. So if you just added the probability of getting a diamond plus the probability of getting a 5, you're double counting the 5 of diamonds. So we need to subtract it off once, not twice. So it's still counted once, but we need to subtract it off so it's only counted once. And that reduces to 16 over 52, not 17 over 52. Finally, the probability of getting a red card or a 7, that's the probability of getting a red card plus the probability of getting a 7 minus the probability of getting both a red card and a 7. So that's going to end up being probability of a red card. There's actually 26 red cards in the deck if you count diamonds and hearts together. So that's 26 over 52 plus 4 over 52 minus there's actually 2 red 7s in the deck. The red of the 7 of diamonds and the 7 of hearts. So it'd be 26 over 52 plus 4 over 52 minus 2 over 52. Right. Probability of a red card or a 7. Going to the dice example. You're tossing 2 die again. Suppose that a pair of dice are thrown. Let E be the event that the first die shows a 2. So that's going to be everything along this row here. The first die is a 2. Let F be the event that the sum of the die is less than or equal to 5. Find the probability of E or F. So this is going to be equal to the probability of E, just using the general formula, plus I need to give myself a little space, plus the probability of F minus the probability of both E and F. And this, I didn't use anything magical. This is nothing magical or unique to this problem. This is just the general formula. But now let's bring in the unique parts of this problem. The probability of E. E is the event that the first die is a 2. It's going to be, I'm using blue here. It's going to be these 6 possibilities. So that's going to be 6 over 36. Now the event F is that the sum of the die is less than or equal to 5. So we got to circle all the ones that have a sum of less than or equal to 5. So this adds up to 2. This adds up to 3. This adds up to 4. This adds up to 5. So all of these are included. But then this adds up to 3. This adds up to 4. This adds up to 5. So these are included, as are these and this. So this right here is going to look like a little bit of a step ladder. Now being circled in red, those are all the cases where the sum of the die, when you add the 2 die together, is less than or equal to 5. And there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 of those. But now the problem is, if I just add those probabilities up, look, these 3 here are both circled in red and also circled in blue. So they're actually being double counted, even though we don't want them to. So there's 1, 2, 3 things being double counted. So the probability of getting both those events is 3 over 36, and we have to subtract it off once. So it's only counted once. 6 plus 10 is 16, minus 3 is 13 over 36. And then you're free to use a calculator to simplify 13 over 36. Put it as a decimal, round it to however many places you need. Here's a little fun brain teaser for you, a fun little math problem. Let's just use our notation properly. if the probability of event E is 0.25 and the probability of an event F is 0.45. So we're not telling you at all in this problem, this is not related to the dice problem. We're not telling you what those are, what the probability experiment is. You can't try to engineer it yourself. Well, just remember this general formula. The probability of E or F equals the probability of E, no matter what E and F are. So then both of these are going to be easy peasy. We want the probability of E or F if we know that the probability they both occur is 0.15. Oh, okay, so that's probability of E, 0.25, plus the probability of F, 0.45, minus the probability they both occur. And a little quick mental math, 0.25 plus 0.45 is 0.7, minus 0.15 is going to be 0.55. What is the probability of E or F if the events are mutually exclusive? So we use this same formula, 0.25 plus 0.45 minus, but now if they're mutually exclusive, what's the probability of this? Of both E and F? 0. Pretty much by definition, mutually exclusive means they can't both happen. Finally, the probability of E complement, remember, we did this notation last time, but E, an event, but then with like a C up there as almost like an exponent, but it's not. This is E complement. That is the event where E doesn't happen. Well, there's going to be a nice general rule here. This is just going to be equal to 1 minus the probability that E does happen. In fact, that's going to be true for all complements. This is going to be a general rule here. The probability something doesn't happen is 1 minus the probability it does. Thus, this is equal to 1 minus the probability of E is 0.25. So the probability of E complement is 0.75. So E complement, it's just saying E doesn't happen. And so this is the complement rule kind of put together. We're not going to spend too horribly much time dealing with it. You can use this apostrophe next to it, or you can use like a C as if the letter C was an exponent on it. Either one of those is correct. They're just different notations, basically, at the end of the day. So if you're dealt a single card from a 52 card deck, the probability that you don't get a queen is going to be 1 minus the probability you do get a queen. Getting common denominators, 1 becomes 52 over 52. So this becomes 48 over 52. One becomes 52 over 52. Yeah, in order to get common denominators. So the complement rule here, very important rule in statistics. We're going to appeal to it a lot, actually, in order to solve certain, I don't know, complicated equations, or not equations, but just, you know, if you go back to that housing example, that housing unit example, if you wanted to know the probability of getting a house that is going to have 2 or more rooms in it, you'd normally have to add up all of these right here, because these are all the probabilities for 2 or more. Or you could use the complement rule and just do 1 minus the probability of a house only having 1 unit in it, of 1 bedroom, I should say. So the complement rule can be used to save yourself a lot of work. So let's say we have a cute little pie chart here. This is the number of people in America in certain age groups who are drivers. They have driver's licenses and they drive. The group of people that are less than 19 years old would be right here, this slice. The group of people in their 20s would be this slice. In their 30s would be this slice. 40s, this slice. 50s, 60s, 70s, and 80 or older. If one person is selected at random, find the probability that the person is not in the 20 to 29 age group. So the first thing we're going to have to do is find the probability that they are in the 20 to 29 age group. I'm going to have to add these all up, though, so I know what the totals are. So 9 million plus 33 million plus 40 mil plus another 40 plus 31 plus 19 plus 13 plus 6. There's 191 total, 191 million technically, total drivers. Now, I could, if I want to find the probability that they're not in the 20 to 29 age group, I could say, okay, well, I got to add up this one, the less than 19, then I got to add up all of these. But that's kind of a pain in the butt. Another thing I could do is just do 1 minus the probability that they are in the 29 to 29 age group, which would be 33 over 191. And you can use a calculator for that. This ultimately comes out to about 0.827. Oh. So it's the probability that someone randomly selected is not in the 20s, in their 20s, that is a driver. If you select one person at random, find the probability that the person is less than 80 years old. So I can either do this. I can either add up everybody who's less than 80. So the 70s, 60s, 50s, 40s, 30s, 20s, and the 19 and under crowd. I could add up all these, or I could just do 1 minus the probability that they are 80 or older, that they are in the 80 plus crowd. So 1 minus 6 over 191. This is the probability of being in the 80 plus crowd. 6 over 191. And that's going to be, give me a moment, 0.969. And I'm rounding to 3 decimal points. So there's a pretty good chance if you randomly select one driver there's a pretty good chance they're going to be less than 80 years old, as you'd expect. So let's do a couple more. According to the American Veterinary Medical Association, 31.6% of American households own a dog. I have a dog, a bloodhound named Shepherd. He's very cute. We're dressing him up as Dumbo for Halloween, and the costume already comes with the big ears, but we're going to take those off because his ears are already massive, and so he's going to be Dumbo. He's going to look really stupid. So according to the American Veterinary Medical Association, 31.6% of American households own a dog. What is the probability that a randomly selected household does not own a dog? Well, 31.6% translates to the decimal 0.316. So if you randomly select a household, there's a 0.316 chance they'll own a dog. Since we want to know the probability they don't own a dog, do 1 minus that. And that's going to give you, what, 684.684? Let me write that better. Pretty straightforward on that one. Nothing too wild or fancy. This last one, the following table represents the employment status and gender of the civilian labor force, but only in their high teens, old enough to have a job, but it's not yet 20, 16 to 19. This might just be in a certain town or something like that. So let's see, there's 2,328 employed males in this age group. There's 2,509 employed females, for a total of 4,837 who in that age group who have a job. There's 898 unemployed males, 654 unemployed females, for a total of 1,552 who are unemployed. Unemployed means that they want a job, but they don't currently have one for whatever reason. And then not seeking employment, well, you know, it's not every teenager, especially if you're like 16, maybe you're not looking for a job at the moment. Maybe you're going to wait till you're 18 or 17, something like that. So there's this many that are just not even seeking employment, 5,416 of which are male, 5,237 are female. And so these are the total males. There's 8,642 males in this age group in this town, 8,400 females. And then all together, there's 17,042 people in this age group here. So if we randomly select one of these people, find the probability that they are male. Well, this one's kind of easy. We can ignore, for the moment, these numbers in here, because bottom line is there's 8,642 males out of 17,042 total people. So it's just going to be 8642 over 17,042. And we'll just draw a little line here and make it a fraction. And so whatever that becomes, you can put that in a calculator. Do 8642 divided by 17,042. You'll get a little over 50%. Find the probability that a randomly selected person in this age group is employed. Well, again, we can skip some of the little individual numbers, and we can say that 4,837 total are employed. So it's going to be 4,837 divided by, again, 17,042. Which, once again, you can decide what you want to do with that information. How do you want to simplify it? Write it as a decimal. Now this one's getting a little bit more specific. Find the probability a randomly selected person is both male and employed. Ooh, so we have to actually get in here and say, oh, there's 2,328 people in this age group, which are both male and employed, but still out of 17,042 total people. So now the numbers are 2,328 divided by 1,742. But now this last one, we have the word or in there, and maybe there's a little trick you can do so you don't have to necessarily use that or formula. I'm not going to try and bypass that. I want the probability of getting a male or an employed person, and it doesn't matter what the context is. If you're doing an or probability, it's always the probability of the first thing plus the probability of the second thing minus the probability of both of those things occurring. Let me expand this. It doesn't matter what context your problem is in. This is going to always be true no matter what your events are. Well, the nice thing is we've actually already constructed each of these individual pieces. The probability of being male is 8642 over 17,042. So look, I'm even just going to come steal it. Yoink. Wait a minute. It does not want to work with me. There we go. I'm going to come steal this pieces. Oh, that's the probability of being male. Probability of being employed is 4837 over 17 whatever. We're going to add them. And then by doing this, we've double counted the group of males who are both employed, who are also employed. So we have to subtract off using that formula one instance of it. And so we do the math. Thankfully, they all have the same denominator. 8642 plus 4837 minus 2328 is going to give you 11,151 over the 1742, 17042. Okay, that's a good place to call it now. Again, this probability stuff, there's a lot of it. There's a lot of it. We're probably not going to be able to get through. We'll finish chapter 5. We probably won't be able to get through chapter 6, just being honest, before our next exam, which will cover chapter 6. So what I'm going to say is I'll leave chapter 6 to you to study. You can actually start studying it right now. There's videos found in the Canvas modules. And then with a little wink and a nod, the chapter 6, or excuse me, the next exam, which covers chapters 5 and 6, it'll be a little bit light on chapter 6. How does that sound? Because frankly, chapter 5 is the more interesting chapter anyways. So I want to focus on it a little bit extra. So let me take attendance real quick. And then y'all will be good to go.